We're starting a new topic today. It's not really a new topic, it's kind of an old topic. You just didn't realize we've been doing it all along. But this is going to take up a substantial portion of our attention from now on. So roughly speaking, for the next month or so, this is all we're going to do. Okay? So the topic we're going to start covering is graphs. And even though math may have invented it, Euler invented everything, I guess, and physicists like to think they own everything, this is like the signal achievement of computer science. Okay, this is like the stuff where computer science really comes into its own, and it's really part of the progression of what we've been doing all along. Right? So what is a graph, first of all? So roughly, it's easy to describe this with a picture. And a graph is a collection of things with arrows. Okay? Now, at a high level, that's what a graph is. So we give names to these things. We call the points vertices or nodes, and we call the arrows links or edges, and there's no standard terminology, so you can use whichever you want. I will maybe even flip between them. I'll tend to use nodes and vertices, but you'll also see links, edges, etc. Okay? Nodes and vertices, links and edges. All right. So that's basically all a graph is. Now, is there something curious about the graph that I've drawn on the board? Talk to your neighbors. Wake up. I want you to wake up. It's Monday morning. So talk to your neighbors and tell me what's curious about the thing I've drawn on the board. Go. Talk. Five, four, three, two, one, and we're back. Okay, somebody see something curious? Everybody see anything curious? Curious. Okay, all the arrows moving in a clockwise direction. Okay, great. Yeah.
There's a vertex all by itself.
Yeah, there's a vertex all by itself. Okay. Yeah.
There's a vertex that points to two different vertices.
There's a vertex that points to two different vertices.
The number of edges coming out of any vertex is not constant.
A number of edges coming out of vertex is not constant, meaning some have, what are the non-constant numbers we have?
0, 1, and 2.
0, 1, and 2. Okay, any other things? Any other things? Any other things? Any other things? Yeah. Hold on, go ahead.
There are vertices drawn as open circles and some drawn as closed circles.
Circles. There's some weird circle thing going on. Very good. Okay. Other things? Anything else? Yeah.
There are no links that go like anti-parallel.
No links that go anti-parallel. What? I don't even know what that
So, like,
means.
There's one that goes in one direction, but there's not a link back to that vertex.
Okay, so is that true?
No.
Where? Point or counterexample. Okay, good. Everyone point. Okay, good. But that's a thing to think about. Hold on. We just came up with an interesting question. We came up with a question we can ask about a graph. Okay? Now ask yourself this. So we've seen several characteristics, right? There's something about clockwise-ness. There's something about cycles. There's something about nodes not being connected. Something about the so I'll introduce this word degree. Okay? So a degree of a node is how many links are attached to that node. Yeah.
Do you mean incoming, outgoing?
I haven't said that, have I? Yeah, and I'll get to that in a moment. All right? So think about the data structures we've dealt with so far. What have we dealt with so far? What are all the data structures we've used? Lists, trees, DAGs, sets, join lists, strings, numbers, images, right? Okay, booleans, good. Okay, now for all of those, I'm going to skip the sort of the atomic data, the data types where there's no reference to something else. Okay, so I'm going to skip the atomic data types. I'm going to pass over strings, images, booleans, and numbers. let's talk about lists and sets and trees and DAGs. Did anyone say DAGs, by the way?
Yeah.
You did say DAGs? Okay, good. All right. Okay, so lists and sets and DAGs. Is it meaningful to talk about the degree of a node in a tree? It is?
Yeah.
Is it meaningful? Well, of course it's meaningful. We can ask how many edges come out of a node. Is it interesting?
Somewhat.
Yeah. So you have like binary trees and then like other kinds of trees.
Yeah. Interesting? Why? Where is it interesting?
Because, I mean, I feel like you can know what type of tree it is. by
Ah,
analyzing the different-
aha. So in a binary tree, what's the degree? 2 or?
Less.
1/3.
2 or fewer. Okay. 2, 1, or 0. Can it be more than 2? No, we have a very strict bound on it, right? Have you seen trees where that might not be the case? Where have you seen trees where that might not be the case, where there's not a strict bound?
File system.
File system, right? Yeah?
About the binary search tree, binary tree doesn't that matter the one on top, the edge on top of the?
Well, yeah. So I haven't even gotten to that question, right? Okay. So let's for now talk about degree being the outgoing count. Okay? So if we talk just about outgoing count, very good point. If we talk just about outgoing count, whole point about binary trees, we're bounded at 2. Right? But with graphs, we don't have bounds. There's nothing that limits the data structure from having a degree of bigger than 2. Okay? But you might say, well, but we did that for trees as well, right? So we saw file system. We actually also saw other things, family trees, right? The number of descendants is not bounded, right? I mean, maybe in practice it's bounded by some number, but it could be a fairly large number. The data structure does. We designed the data structure to not have a strict bound. Updater, bounded. Updater, bounded, not bounded. Not bounded or not sure? Go think about that question, okay? So we can talk about some of these questions. Do we get trees where there's a node that's completely isolated? Is this a sort of yes, sort of no kind of thing? Sort of yes. Okay, question, we're going to vote. In a tree, is it meaningful to talk about a node that is completely isolated? Okay, nothing coming in, nothing going out. How many vote for yes? How many vote for no? Wow. Okay. Why yes? It sounds like you should be able to make your case with a concrete example. Can you make your case with a concrete example? Make your case with a concrete example?
If you got like the root that has no children.
A root? Root? Okay. Any other interesting examples? Yes?
I would say that the isolated node is its own graph, like it's not part of the first.
We're talking about trees. Let's just talk about
Alright,
trees. We're
it's
talking about
its own
trees.
tree.
It's its own tree, but that's the same as the root,
Yeah.
right? Okay, so do you have a non-trivial example, an interesting example? You can't actually, right? The whole point about trees is they are what are called a connected data structure. We're going to get into all of these things as we go along, okay? They're connected. They're not disconnected, okay? That's one of the things that makes graphs interesting. Graphs, it's perfectly legitimate to have a disconnected vertex or node that's not connected to anything else, okay? And it can be even weirder. You could have a vertex or node where something could come in but nothing goes out, right? It's like the Hotel California vertex or something like that, right? So, sorry. So all of these are completely legitimate from the point of view of a graph data structure. So in fact, I'll draw one of these as well. So, and there are names for these things. We'll learn about the names as we go along. Okay? So that's a pretty general structure that I have there, right? Right? So there's some tree-like part to it. There's a thing that things only go out, things only come in, things where nothing goes in, nothing comes out. Okay? These are all allowed by the general notion of a graph. Okay. Now, here's what I want you to do. I want you to talk to your neighbors for the next few minutes, minute or two, And I want you to come up with examples of things that make sense to be represented as graphs in their generality. Okay? Because what's going to happen then is I'm going to say, really, if that's a graph, you should be able to give me an instance of something where it's actually meaningful to have only incoming edges, only outgoing edges, or no edges at all. Right? That's when you're really exploiting the full power of a graph. Right? Because otherwise, maybe it's just a tree, maybe it's just a DAG. Right? So I want you to think about examples of graphs that really exploit the graphness. And I'm warning you that I'm going to challenge you when you say, I think X is a graph. Like, really? Then give me examples of this. So be aware of the challenge and prepare for it. Go.
And then you can have, obviously, they don't have very high degrees. Like some people have some problems, but the problem is you can
All right, in 5, 4, 3, 2, 1, and we're back. Let's do it. Let's go by groups. Let's start over here. Go. Give me one example.
Instagram followers and following.
Instagram followers and following. Okay. I've been told that nobody is on Facebook anymore. Kids like you are all on Instagram, so you've proven it. Okay, why do you think Instagram is a graph, not a tree or a DAG? What is an example? Let's get partners talking.
You can have no followers and you can follow nobody.
You can have no followers, right?
Yep.
But typically, bots are not that, right? Right? Because bots manufacture followers. So you can have no followers, right? Maybe you're very unpopular. But how do you follow nobody?
You just don't.
Maybe you're a celebrity, right? You're not going to bother responding, right? Okay, so Instagram certainly seems to be an example of this. Could you have cycles?
Yes.
Meaning, right? You can have certainly a pair of friends who follow each other. Next example. You three together? Go.
One we had was a diagram of airplane routes between airports.
Airplane routes, okay. That seems a bit controversial. Airplane routes. So this is really airline, right? It's airline routes. How would you have a node that has no edges in airline routes?
No flights. Storm.
Hold on. Storms are talking about the dynamic configuration at a given instance, right? We're talking about airline routes, meaning we're talking about the thing that's in the back of the magazine, right? That's just describing their standard routing, right? Anyone from Worcester? Well, I mean, so cities lose their commercial airlines sometimes. Like Worcester lost its airlines at some point, right? No commercial airlines. I think there's still private aviation, but so you can have a city. I mean, there's lots of places in the world. In fact, like Pawtucket, for instance, does not have any airport. So, or actually, there's a North Central Airport in Lincoln, Rhode Island, that has no commercial airlines, right? So there are airports that have no planes coming in or going out from the point of view of that airline. Okay, so clearly there are cycles, right? Could you have a weird thing where there's a plane that only comes, like, what would it mean?
Plane factory.
They have an airport factory, right? Could you actually have a thing, like, this is like the graveyard in the Mojave Desert, right? Planes go in and never come out. Yeah, but what you can imagine something like this, right? Something like this. There's actually like places, some places like the Virgin Islands, for example. I believe that happens, right? So you can come in, but you can't go back there. You can only go through. So they run only triangular flights. They don't run direct round trip flights. So if you want to get from here to here, you either take a boat or you do something else, right? Okay, good. Next group.
Like in a sentence, words like depend on each other.
Oh, sentence. Wow, that's a great example. Sentence. What are word dependencies in sentences?
Predicate.
Predicates. It's actually an interesting term called anaphora. Anaphora is indirect references. So when you say his or hers, theirs, right? You're referring, you're not saying exactly what it is, you're picking up a reference that was previously stated. Okay? So sentences, can you have cyclic dependencies in a sentence?
It should be possible.
Well, I mean, you could also have weird sentences like this sentence is not true. Right? That's a reference to the sentence itself. So conceivably, sentence is a very interesting example. Next group.
I feel like this is a basic one, but we were just talking about maps. Like, it's really meaningful to
Maps.
analyze places where, like, there are no connections between, like, destinations, because then you...
So let's, hold on. So when we talk about a graph, we have to be clear about what the nodes are and what the edges are. So so another person in the group, what were the nodes and what were the edges?
The nodes are destinations
And edges are?
roads.
Roads, okay, good. So maps where you have cities or towns or whatever, and you have roads, right? So you always have to be clear about what the nodes and what the edges are, right? So you could definitely have disconnected cities and so on, okay? Any other examples in the class? Anyone else? Because I feel like we may have run, yeah.
Computer networks.
Oh, computer networks, yeah, like the internet. Right? Okay, internet, and so is that, you can have cycles on the internet. In fact, you kind of better, right? The whole point is redundancy. Can you have an isolated node? Can you have a node where everything comes in and nothing goes out? Yeah, okay, all right, okay, yeah. Sooner or later, someone's going to mention, like, Russian bots or something. So yeah, absolutely. So this is, in fact, like a sort of canonical picture of a network. Yeah.
Like a sports league schedule.
Sports league schedule. Okay, tell me more. You need to tell me sports league schedule. Says the person wearing a Boston cap, right? So nodes and edges. What are the nodes? What are the edges?
The nodes are teams, edges.
Nodes are teams, and the edges are?
So if one node points to another, they have an away game at that.
So plays is basically, right? And plays at is the direction, right? Okay, is that, yeah, okay, good, yeah.
You could surface level water flow.
Oh, water flow, okay, awesome, water flow. Okay, and what are the nodes and what are the edges?
Nodes are going to be like geographical regions, and then the edges will measure how much water is flowing from one region.
So the edges are basically direction of flow.
Yeah.
Right? Okay. Okay. So these are all great examples. Notice, by the way, that we're also starting to talk about some characteristics. So there's a question of whether the edges have to have arrows on them. And think about a highway, right? Highways it's pretty rare that you have a road going one way. I mean, we do in cities, of course, we have one-way streets by definition, right? But they have a special label because that's not common, right? Usually you don't build an interstate from one city to the next and not give people a way to come back, right? So many times edges are not directed, meaning if you can go in one direction, you can also go in the opposite direction. Now, let's think about this for a moment. Which one is more general, directed or undirected? Talk to your neighbors. Directed or undirected? If we had to pick one to use in this class, should we pick directed or should we pick undirected? Go.
Every time you do it, you should want to do it.
Okay, voting. For voting, how many of you vote for undirected? Okay, directed. Why? Because you can. What's the key word?
Make it.
Encode. Encode. Okay, you can encode. You can always encode an undirected graph in a directed graph by simply having directed edges in both directions. You can't easily encode a directed graph in an undirected graph because you've already lost that bit of information. Okay? Yes?
Can you necessarily say that, like,
We don't need an additional piece of information saying this is an undirected graph because in some situations you don't want to go both directions along an undirected.
Then it's not undirected anymore. By definition, that's what undirected would mean.
You don't want to. Oh, you don't want to travel along the same undirected path twice. How about that?
That we haven't talked about traversals, right? Like that's fine. I don't see an issue with that. Yeah, I'm not sure. Let's take that offline because we may have a point there. But I'm going to pick directed edges. Okay, and if you have to make an undirected, well, you just put both the edges in. Okay. As you also notice that, well, I mean, in maps, right? If you talk about the roads, they also have information on them. They have.
Names.
Well, they have names, but more importantly, they have weights. They have like how much, what is the distance between these two things, right? And it might represent different things. It might represent the distance between them. It might represent, what else could a number that I associate with a road represent? It could represent distance.
Speed.
Anything else? Speed limit, yeah?
How many lanes?
How many lanes?
Cost.
Like a toll, right? Anything else?
Volume of traffic.
Volume of traffic?
Time to travel.
Time to travel?
Direction.
Well, we've already said they're directed edges, right?
Geographical direction.
Heading.
Yeah.
Bearing, orientation. Okay, like is it going northeast, which are like what's the compass angle? Great, okay? So the point is we have to always be careful about our interpretation, okay? One thing could represent many different things, so you've got to be explicit when you say what these things represent. You have to say exactly what it represents, okay? Okay, so the critical thing about graphs is they could have cycles. Okay? You can start from a point and get back to that point, and that's not a thing you could have with a tree by definition. That's what makes something a tree. You can't get back to where you started. And you can't really with a DAG either, right? Because a DAG is a directed acyclic graph. By definition, it's acyclic. Okay? The problem with cycles is that if you're not careful with the algorithm that you write, you will not terminate. Was that a problem with a DAG? What was the problem with DAGs? Was the problem lack of termination?
No.
It was something a little more subtle, right? What was the problem?
Couldn't keep track of what we already saw.
Yeah, well, no, but what's the problem? What if he didn't do that? What went wrong if we didn't do that?
Double count.
Yeah, so we get this double counting, right? We don't get a correct accounting of the thing, right? If we're computing the size, if we're making a copy, we're not completely faithful to the original, but all that happens is we just duplicate things, right? We duplicate the count or we duplicate the nodes or something like that. We don't go into non-termination problems. With a graph, it's now critical. It's not just a luxury. It's absolutely critical because if you don't keep track of what you've already seen, you will literally go into an infinite loop. That's sort of the defining characteristic of a graph. Okay? Make sense? Questions so far? Okay, so we're going to be spending a lot of time on graphs. I want to make sure we build up an intuition. Some of you may have seen this stuff before in school, maybe in this form, maybe in different forms. Some of you have not, and that's okay. I want to build this up slowly to make sure we all come along on the same page. And it's so important, it's so vital. As you can see, it represents so many different things that really understanding this is central to doing good computer science because so many things get encoded as graphs. Right? Like Facebook is basically a giant graph company. Right? That's all it is, right? Social networks are giant graphs. And in some sense, so is Google, right? The search engine behind Google, what's it doing? It's actually making a copy of the internet graph and running a whole bunch of algorithms on those graphs, right? If you look at the kind of information storage that Palantir seems to use, seems to be all about graphs, right? Amazon, collaborative filtering, which you did in your first assignment, Nile. Well, what is that? That's basically you generalize that problem a little bit, you turn it into graphs, right? I'm recommending to you, but you're actually also recommending to me at the same time. I mean, I'm not actually doing anything, but Google, Amazon is giving me no choice in the matter, right? Netflix, recommendation system, right? It's using my all of our recommendations to recommend to you, but your recommendations to recommend to all of us, right? Again, there's this graph-like property to these things. So there's graphs everywhere, everywhere. Okay? All right, good. So that's why I want to take it easy, step by step, and build up our knowledge as we go along. Okay? And two terms that you will see is source. So in a directed graph and an undirected graph, it's meaningless. A source is a vertex that has only outgoing edges, and a sink is a vertex that has only incoming edges. Okay. How many sources in this graph? Yell out a number. 2? 3?
2.5. What about the set alone?
So, 2 or 3? Vote for 2. Vote for 3. Okay, can we agree on the 2? The twosies, who are you? Who are the 2s? Which are the 2s? Point.
Yeah.
There?
A little bit up.
That, okay. And what's the other one?
Right.
That one. Where did the third people see a third one? Point. Right there? Right there? Yeah, it's not entirely clear what to do with that, right? So you could say that as a base case, it's also a source and a sink, right? Or you can say it's a trivial source and sink, it's not a non-trivial one, right? Doesn't really matter. But we won't be using, I'll only be using these terms casually in class. It's not going to be a definition that it's going to be, exemplar is not going to care about sources and sinks, right? So none of your tests are going to go wrong because we didn't agree on the definition. So I prefer to include empty things because it just makes all the definitions, the math a lot cleaner. And then you can talk about non-trivial sources, non-trivial sinks. Right? Good. Now, before I go on, I want to do a quick activity in class. People have pens? If you don't have pens, I'm going to do an in-class quiz. Okay? Oh my God, I know. He never said he'd do that. I'm not going to, you don't have to write your name on it. I don't want to know your name, actually. There's no place to write your name. It's really, let me just explain, it's really a sort of elementary math assessment. Okay? And I'm trying to understand something about learning going on in this class. So let's do about 5 to 10 minutes. We don't need more time than that. And I have spare pens, so please pass these around. Pens, so pens might be better. I'm going to use some software to look up answers and stuff, and pens will work better. So if you need a pen, let me know, and I'll give you a pen. Anyone got extras? Extras? Pass the extras around. Who's missing one? Raise your hand. Who has an extra? Okay. Thank you. Yeah, pass it. Thank you. There you go. Okay. Who needs a pen? Do you need a pen?
Maybe a pencil.
No, I'd rather use a pen if you don't mind. Thank you. Anyone need a pen? Okay, good. You need. There you go. And the last question's a little hard to read, so I'll just write some stuff out on the board. So when you get to the last page, look on the board. when you get to the last page, I've redrawn the picture here. There's a missing item there that I've filled in there, and just skip the follow-up question on the last page. You can skip the explanations too on the last one. So on the last page, the second bullet is kind of finished. It's finished over here. Skip the explanations and skip the follow-up question. Sorry, this is the last page. This is the second entry. There's a dot, dot, dot that kind of got screwed up. So, sorry, this is in place of the second entry, the one that got screwed up. Yeah.
Do we get any more information about the drawing than what's given, or just scope?
Well, sorry, that's 1 inch. And that one is, I think, 2 inches. Yeah,
It doesn't say that.
It doesn't say that, right?
Doesn't really say.
Yeah. Tell you what. You know what? Skip question 5. Skip question 5. This is a little hot off the presses. Skip question. Just skip question 5. If you haven't done question 5, if you've done it, that's fine. If you haven't done it, that's just fine. Skip question 5. People are mostly done then. Mostly done. Anyone need more time? I'll give you another minute to finish up, and then we'll stop. If you need more time, just point your hand up. Okay, great. Okay, could you just move all of your answers down to the middle, and then we'll just collect them up the middle? I don't need names. I don't want names. Let me tell you why we're doing this, by the way. It's kind of weird, right? So we've been on a kick for the past several years. Computing curricula for the past 60 years have been designed basically as a matter of opinion. Okay, everybody's convinced that they know exactly what needs to be taught and how it needs to be taught, and then, you know, the only assessment we do is essentially we give an exam. Guess who wrote the exam? Right? So you teach to your exam, and that's not necessarily a bad thing, but it means that we don't actually understand a whole lot about learning. And so I've spent the past 6-7 years immersing myself in cognitive psychology literature and educational literature, trying to understand, like, how do we know when somebody has learned something, and what does it mean to have learned, and what does it mean to assess? So what we're trying to do at Brown is essentially buck the trend and create, it's going to take many years to do this, but create what are essentially research-driven curricula, right? Basically investigate learning, figure out how we can be more effective, where learning succeeds, where learning doesn't succeed, what are the prerequisites, what are the things that students might be stronger at, weaker at, and use all of that information. And in some sense, every course is actually a research experiment. Right? Why do we put an assignment in? Because we think that assignment is going to work. We think it's at the right level and there's some learning that's going to happen. And sometimes we get it wrong. The assignment's too hard or the assignment's too easy, and we find out after the fact that we go and adjust it. What is that? That's essentially how an experiment works, right? We try something out, we collect some data on it, we find whether it works or not, and then we adjust it. So that's how every course is designed. So every course is a research experiment, except it's never run as one. It's never formally run as one, and so it's sort of ad hoc, like, they didn't do it, they must be stupid, right? You just move on, right? And so what we've been trying to do at Brown is actually not do that and actually try to collect data, try to use instruments, try to find ways to understand student learning. Also understand student learning other than just at the level of how the homeworks are going, okay? So this is you know, if you're frustrated that you're an experimental subject, good, well, you know, news, you always are an experimental subject, right? In all of your other courses too, you're an experimental subject. Every professor, hopefully, studies what happens in that course and revises that course, right? So we're trying to do this a little more formally, and we're trying to design instruments that might help us understand a little more about the class. But I'm not trying to learn anything about any one of you, right, personally, which is why I don't want your names on these. We're just going to look at aggregate information and see what we can learn, right? So that's what's going on. Does that make sense? Okay, good. So it won't help you directly, maybe not, but it'll certainly help next generations of the classes as we try to use this kind of feedback to improve what we do. Okay, good. So if you could just pass these up down the middle from back to front, that would be really great. Thank you. And just bring them up to the front, and then I'll collect them in a moment. One more. All right. Thank you very much. So now I want to get back to dealing with graphs. And for that, I'm going to change my display control. Unmute my video. So there are two more things I want to do. The first is talk about how to represent graphs. Now, the fact is you've actually represented graphs already. Really? You remember we did an identical test on the streams, and we asked, is, you know, the rest of the stream identical to the whole stream, and the rest of the stream, is it identical to the whole stream? Remember that? Similar to the things that you did for your continued fraction homework? Well, if it's identical, what that means is when you traverse it, you are getting back to where you started. It's a cycle. There's actually, honest to goodness, a loop in your memory where something points back, eventually points back. If you follow the references in your memory, you'll get back to where you started. That's what the identicalness tells us. That's literally what it tells us. Okay? but that's a kind of awkward representation, and certainly it's something you won't use in other courses. So I'm going to give you more conventional representations. It's not interesting enough for me to derive these, so I'll just tell you what they are. So a few different ways, and individual assignments might tell you how to do things in different ways. So one of them is to simply have a graph as a list of nodes, and every node has a key, okay? It's got some string telling me like how to find it. So in an airport network, for example, that might be the airport code, right? Like the 3-letter code for the airport. And there's some content, which is the actual payload. And then, so just like we have a value in a tree, this might be some additional information, some metadata. And then finally, a list of other things that it's adjacent to, right? Now the critical thing is, it's not a list of nodes, it's a list of strings, right? Because if we made a list of nodes, it'd be very hard to actually construct one of these, right? If I had 2 nodes that each refer to each other, you can't make either one first, right? What the string does, what the key does, the thing it's called a key, does it gives you a level of indirection, right? So I can write down a string like PVD for Providence, and its adjacency list is a list that includes a string EWR for Newark. And then I can write EWR for Newark and a list that includes PVD for Providence to represent the fact that we have flights between the two, right? And each one you can construct on its own. You just have to make sure what? What needs to hold at the end of the day? Yeah?
They need to both have each other.
If you're trying to represent an undirected graph, you need to make sure that both of them are referring to one another, right? Yeah?
So if a node has like another string in its adjacency list, then does that mean that it's pointing to that node, or that that node's pointing to it?
So I'm going to use it to mean this is pointing to that. Okay? The adjacency is the out degrees. Okay? There's actually a more subtle thing you need to make sure. You need to make sure that every string that is in here is actually a legitimate key. Right? Like typos are actually a problem now. And in the real world, when you get real world data sets, that is actually a non-trivial problem, because there's human operators entering data, and when human operators enter data, they always get things screwed up, and you end up having to cleanse your data to clean up those kinds of things where you have a reference to something and it's not even here, right? Or even worse, you might have lots of things there that say EWR, and while typing EWR, they typed EWK or something like that. So there's lots of references to a non-existent thing, and there's a thing that has no references to it, right? And you have to fix those kinds of things. And you too will make those mistakes as you write your homework. So, okay? Okay, so that's one kind of representation. It's a second kind of representation that I'm going to call an indexed representation, where basically what's different, we still have the content, we still have the adjacency, but we don't bother storing a key. And that's because our keys are going to be numbers, and essentially they're going to be the position in the list. You can imagine a list, you can imagine any kind of index structure, like a list or an array or something like that. And what you're doing is you're figuring out the position. So this might say my adjacency is 0, 1, and 4. Right? And you have to go to 0, 1, and 4 to figure out what they are. It's sometimes a very efficient way to do things. It's also an incredibly error-prone way of doing things, because like 0, 1, and 4, there's no way to audit that and check whether that makes sense or not. Okay? So that's another standard representation we use. And if you think about this a little bit, if you think about each thing is a list of numbers, and there's a list of numbers, that's basically a matrix. Okay? And it's very conventional in computer science to use matrices to represent the adjacency, which thing refers to what. Okay? There's a third representation that will actually be relevant in about a week and a half. It turns out to be just the right representation for that, which is to have just a list of edges. Right? Instead of saying the main thing is the vertices and then the edges are things that come along with the vertices, you flip that perspective and say the main thing is the edges and the vertices just exist to give the edges a place to start and end. Right? And that's what that's the list of edges representation. And so what is a graph? It's just a list of edges. Okay? And it's got a source and destination. And again, you need to make sure that the source names and the destination names are actually accurate names. Right? Does that make sense? Okay. All of this is explained in the book. This is the chapter on graphs. And so we're now into 1923, okay? And basically what I'm going to make you do is use these graphs without worrying about the representation, just as we've done before, right? We did this for sets, you recall. We've also done this now for lists, right? That's what you're doing for homework. And so we can think of graphs the same way. There are multiple possible representations. Each has some strengths and weaknesses in different settings. We're just going to focus on an abstraction of them that basically says, given a vertex, give me all of its edges. Give me an edge, tell me where it's going to. Okay? Make sense? Questions about this? So we're starting to do graphs. We're gonna, so I would like you to read, actually read the textbook up through 1924. Okay? Up to abstracting representations. We'll continue with the rest of it in class next class. All right, see you next class. Could I just get those bundles, please?